就这边 I think so. I think
one method of determining your stiffness matrix. Yes? So, having said that, this is now your solution. So, it's very, what do you call this one, straightforward because you just integrate, but because there's a lot of parameters involved, then it's too troublesome to really determine the different values. Okay, so hopefully you were able now to at least touch a bit and be able to understand how we got these values really. So why do we have the so-called standard values? And those standard values are based on your shape function. So once you change your shape function, your stiffness matrix change. Yes, so your stiffness matrix, which is given by this one, is only based on the assumption of your shape function. So your shape function that we use is this Hermitian cubic polynomials. If you change this shape function, or the previous one that we had in the morning, if you change that, then you will have a different stiffness matrix. Okay? So your assumption or your solution, you must know why you have the answers. Okay? It's not because wrong calculation or a wrong method, but because these are all based on a certain assumption. So let's move on. I'd like now to have a look at the PVD that we had earlier. Let me correct myself there. Earlier I had this, we have U equal to N1 U1 and U2. So this is just for a bar. Let me just correct myself here. So this one is for a bar. So that we have this one to be N1 N2 U1 U2. Just let me put it there. So your matrix will be that the transpose multiplied by UI. That's why you have the transpose there. That will be U. So this one will be specific for a bar. Now let's move on to a beam. So how do we solve the, so you have the principle of virtual displacements already in Moodle. You had that in your year 3 or year 1 that is. So you have all these solutions there to come up with this equation of stiffness. Now let's move on. And have a look at this beam structure. So what's important to know is that you have your curvature, okay? So you understand the definition of curvature. You have your slope, which is this one here, and then you have your deflection. So no worries about this one. This is just some figures here. So I'm just saying that this is the curvature, that is the radius, and the inverse of the radius will be your curvature. So here, I'm just trying to present a few concepts here. That's the trying to increase our vocabulary here. So you have R, which is the radius of curvature. And then the inverse of this one, 1 over R, is your so-called curvature. So no need to worry about that. That's a very simple vocabulary there. You have your slope equal to the first derivative of your displacement with respect to x, and then of course you have your displacement or deflection there. So the thing that I want to look into now is your PVD. So we have done a PVD with the bar already. So I think what you need to know is this one here. Your M all over I equal to E all over R equal to sigma over Y. So this one is a classic equation for a beam wherein if you want to determine the stress for beam bending, then that is sigma equal to My over I. And here you have your stress equal to E multiplied by K. Or, for example, you have now here your Mi. So just allow me to put positive values for everything. So this one is a very classic equation for a beam, wherein if you want to determine your stress for beam bending, you have My all over I. If you want to know your constitutive equation, that is sigma equal to E divided by R, but this one is the inverse of K, so this one is E multiplied by your curvature K. And this one here, that K, is the second derivative of your displacement with respect to X. So this can be written as E, second derivative of U with respect to X squared. So this is specific for beam. Right? This is just for beam. So what do we use for a bar? This one is your strain. Yes? E multiplied by the strain. So you get a different stiffness matrix. So this will be our rationale for this one. If you solve for that stress, that will be your E multiplied by that curvature. That curvature is the second derivative of your displacement with respect to X. So what is your displacement? This is your transverse displacement. So we'll keep it that way. So again, here you go. So you have now here stress multiplied by the strain. So we got this one already, your PVD. So this one is your work minus the strain energy is equal to 0. So your work done, force multiplied by the distance, is equal to your stress multiplied by the strain, the area under the that rectangular curve. So substituting the constitutive relation for a linear elastic material, you have now this one to be E multiplied by your strain. And your strain here is equal to this one here. So that's why we're going to use that K there. So minus Y, this one here, because this one is virtual, you use a virtual curvature. Yes? So this one is that, E multiplied by strain. This one is that. This strain here is equal to minus Y over R. That virtual strain is equal to minus Y all over the virtual radius of curvature. So this is the virtual value. Of course, you also have that virtual displacement somewhere here. Okay, so it's similar to what we had earlier. So here we go. Force multiplied by your virtual displacement minus this now equation, so you expand it now. And then you can work on this one, so that is now K multiplied by virtual K, dA. So, okay, this term here, I'll just note Y squared dA is equal to your modulus. Y squared dA is equal to modulus. Just accept that in the meantime. So this is Y squared dA, that is equal to the modulus. So you have now EI K curvature, virtual curvature, dx1 equal to 0. And then you simplify this one, EI equal to D, you have now this one here. So DEI is the flexural rigidity. So let's try to compare. So you have now this and you have now that. So this now is for a beam, you have now this one and you have now that. So this one will be your M, and this one will be your virtual curvature. This one is your virtual displacement. So now the question here is what happens with this one here? So your curvature is equal to this one here, B U or B transpose U. And this one is the second derivative of your displacement with respect to x. Yes? So you can write now this one to be second derivative of n with respect to, or second derivative of n with respect to x multiplied by that u. So what I'm saying here is that you have now this one to be second derivative of NP multiplied by that UI. Yes? So this one now is equal to a second derivative of that N transpose dx multiplied by your UI. And this one now will become your B transpose UI. B is the second derivative of your shape function with respect to x. So you have this notes anyway, just follow, try to follow. So this K now is equal to that B transpose UI, U2 because it's transverse, and this now is B transpose multiplied by that virtual displacement. So like I said, your virtual displacement is a simple identity matrix. Since our total degree of freedom per element is 4, one displacement, one slope per node, so that's 2 multiplied by 2. So we have now this one to be an identity matrix of 4 by 4. So you multiply 1 with this guy, multiply 1 with this guy, then it's the same value. There. And this one again is a scalar value. So what you're going to do is transpose the whole equation. So this one is a scalar value, that is that. Transpose the whole equation. Since this one is a scalar value, it doesn't change. Only this will be transposed. So after that, you rearrange and then you get this B, D, B, E, dx1 or dx, and then that is multiplied by your u2. And then you have your f equal k multiplied by u. So that's how you get this stiffness matrix. Okay, so it's the same procedure as what we did. It's just that the difference is that we look into your strain value. Your strain is equal to, so your strain is equal to y multiplied by that curvature k. So here, this is how you do it. And then of course, after doing that, you can look at the different shape functions. So here, we use the shape functions, permission, but instead of using the x, as what we did earlier, we did a permission cubic polynomial using the c. And we didn't integrate from 0 to L, we integrated from -1 to +1. So these are the difference. So why do we do that in the first place? Well, the first thing is we want to, well, numerical methods is basically using the computers. If you're just using manual calculation, you can use the X space. But if you want to have a good program or code, then you have to use this -1 plus 1, this C space. Okay, you need to do a mapping. So the thing here is that for beams and bars, it's just one-dimensional, it's simple, straightforward. But if you're going to move to higher ordered elements, then it's really helpful to have it's really helpful to map all these things so that you'll just go into the numbers. You'll see that later. Okay. So from this one, of course, you will be getting the same thing that we were able to derive earlier using the shape functions that I gave you. Okay? So, any questions before we proceed with the other discussion on finite elements? So let's now discuss the different reasons why we had to perform finite elements. So one of the reasons why we had to perform finite element is we want to reduce the time of development. So we have this so-called simulation-based design, wherein the previous processes we have the concept, you design it, you build it, you validate it, and then you produce it. So the thing is, this part here becomes very expensive because aside from doing the prototype, once that doesn't work, you go back again to the design board, you do another prototype, and then it's a very expensive process. While if you have simulation, you can reduce this designing and validation before you even do a prototype. So that's the purpose of simulation. One of the methods, or one of the numerical methods that are being used in simulation is FE or CFD. Of course, you have the finite difference method, but for structural, you don't normally use that. You use the finite element method. So, for multinational companies, it's very common. It's very common to use softwares, whether it's GE or companies like wind turbine companies like Vestas, which is #1 in the world. We have been using a lot of finite element simulation models to be able to come up with a better design. So GE as well, Rolls-Royce as well, using a lot of this simulation or finite element modeling and simulation. So again, we have been talking about simulation. If you try to look at this one here, your model will be largely dependent on how you mesh your model. So in this case, if you need a sphere and your mesh is sparse, definitely you'll get higher errors as compared to when you are using finer mesh. Yeah, so take note that finite element is an approximation method. So if it's an approximation, then definitely there will be errors. So what we have to do is, of course, to use different elements. Higher order, the better, but that will also cost a lot to our computational time. Use more elements. Again, the more elements you have finite, the more elements, the bigger stiffness matrix you're looking at, the more equations that we are going to consider, and definitely that will increase the computational time. Yes? So what we did earlier in your Mechanics 3 is to simply look at this 1D structures, meaning just skeletal structures. We have the bars, beams, frames, and trusses. So here we're going to look into 2D elements. You have already an experience in working on 1D as well as how we derive the stiffness matrix. We're going to do that for 2D. So for 3D, you have an opportunity to do a bit of this work in your second project. Just a very simple beam element, 3D beam. So again, there's so many finite element softwares out there. So we're using Abacus as well as ANSYS. SolidWorks has a finite element, but whether it's a good FE, we don't know. So we have a lot of this finite element. So as you can see, this one starts from the real world to a simplified physical model to a mathematical model, and you have now your discretized FE analysis model. Again, there will be a lot of errors because there will be some simplification. Once you simplify, you further make assumptions in the mathematical model, and then you discretize in your finite element model. So in each of these steps, there will be assumptions, there will be simplifications. So the real world, if you're looking at a pail, you probably will just get a cup in the end. So you have to be realistic in the expectation of your results. Why it didn't capture the reality? Because of course, you have a lot of simplifications as well as assumptions made. Yes, so we've done this one already, cross elements. So I hope you're ready now with the 2D elements. So you have now your quadratic element as well as your linear element. So linear, your shape function or your displacement function is simply linear, while this one here, if you're going to use this one, your displacement function will include x squared or even higher. While this one is simply an x and y, while this one is x squared, y squared, and so on and so forth. So we have done that already. Especially this morning where I give you a displacement function or a shape function, then you will be able to have a feeling on what to expect from this quadratic element. Isoparametric quadratic elements. Take note, how many nodes do you have per element? That is 8. How many nodes do you have here? That is 4. Assuming you have a 2 degree of freedom per node, x and y. So for this one, 4 times 2, you have 8 degree of freedom per element. this one you have 16. So just imagine your stiffness matrix. So the more accurate you become, the more computational time you will use. Right? So you have to have a balance. So this one here is linear, this one here is quadratic. But this quadratic here will be able to capture bending. So what happens if you want to capture bending using this one here? You increase the number of elements. Yes? So here, say for example, I want to capture bending or bending of a plate. Right? And these are all linear. Chances are I won't be able to capture much of that bending of a plate because my elements are linear. So what do? I reduce the size of the elements to be able to capture that bending. But that doesn't really make sense because if you increase this one, there will still be a lot of errors, plus you will be increasing your computational time. So it's better to use elements that are able to capture those bendings. Something like that. So with this higher order elements, you will be able to capture the bending of your plate. So if you use linear elements, just like the four-noded quadratic element there, to be able to capture bending, you need to use a lot of elements. But if you use quadratic elements, you can use a lesser number of elements and still get the same results. Okay, lesser computational time, although more because you have more nodes per element. This one is you just have 4 nodes per element, but in the end, this analysis will still be faster and more accurate. So that's the reason why you have different types of elements to choose from if you're going to use finite elements. You probably have realized that in your report already, or first assignment. So you have CP4, yeah, and then you have CP8. So which one is more accurate? So as you can see, the more nodes you have, and it captures it captures the deformation. So the more nodes you have, the more accurate it is per element. Okay, not the whole one. Yes. So that's the thing about finite element. Now here we are now. Again, we're going back to the PVD again. But again, this one is a lot simpler than the beam, because if we're looking at quadrilateral element, linear, we're simply looking at extending the principles or concepts of a bar. So it's the same. You have now here your stress multiplied by that strain, dV, equal to that force multiplied by your virtual strain. So we're now applying this PVD again to this quadrilateral element. Simple one, just very simple one. So your force is equal to K, 8 by 8 by 8 by 8, because we have 2 degrees of freedom per node, X and the Y. Yes? for a quadrilateral element, we simply have U1 at 1 and U2 at 1. So this one is just for a plane. So we have 2 degrees of freedom per node. So you have 1, 2, 3, 4 nodes. So you have a total of 8 degrees of freedom per element. So this one is for a quadrilateral element. So that's why here you have your forces to be 8 by 1. Your stiffness matrix is 8 by 8. And your displacement is a column vector with 8 rows. So your stiffness matrix, 8 by 8, will be equal to the volume integral of this strain displacement matrix and 8 by 3. Your stiffness matrix, so this one now is not just a simple scalar value. This one now is your 3 by 3 stiffness matrix. And then of course you have the transpose integrated over its volume. So that's how you get it. So this one has been derived using this TVD approach. So what are your stiffness matrix? It's this one here. Have a look. This one is equal to that. So it's not anymore just a single value of stiffness. It's that 3 by 3 stiffness matrix. So to simplify, it's equal to this one here. So here, for each of the nodes, it's here, U1, U2, which is your UI. So here, what we're going to do is to perform an interpolation to be able to get that, your interpolation function or your shape function n. So here you go. Say for example, I want to get a displacement somewhere at a point P within my quadrilateral element. So what do I do first? First is I do an interpolation here with my displacement here. I perform an interpolation here, second interpolation, and I do my third interpolation here to be able to get that displacement at point P within my quadrilateral element. So 3 interpolation. One is to interpolate the displacement at that point M, which is in between 1 and 2. Another displacement in between 3 and 4. I can do that. So I get now my displacement and then I interpolate that to get my displacement at point P. Of course, nobody's preventing me from taking the interpolation 1 to 4 and 2 to 3 and then take the middle. So this is how very troublesome a quadrilateral element is. There you go. So you get your UM here first, interpolate to get that UM, and using your U1 at 1 and U1 at 2. So you get your U1. Okay? So you get your U1M. After that, you get your U1 at N. So your limits will be U1 at 3, U1 at 4, and then of course you have your X's. So you get your U1N. So after this one, you interpolate again to get your UI, which is given by this one here. Yes? So you perform interpolation 3 times to be able to get that, and then of course you simplify, you get this equation. So from this equation, you will now get your shape functions. So for bars, you just have to do one interpolation and you will be able to get your shape function. But for this one, you have to perform 3 interpolation to be able to get that shape function. So u1 equal to n u1 plus n u1. So you get now your shape function. Mapping. Why do we map? So here, the reason why we map is because we want to have a so-called strong program or code. Because once you have the code, all you have to do is to put in the coordinates of your element. So as you can see, this one is your actual element, but in the computer it will read as this one here, perfect quadrilateral, perfect rectangle, wherein you have this one to be 1, 2, 3, and 4. So this one will be from -1 to +1, -1 to +1. So this will be C1, C2. You have X1, X2, map to C1, C2. So that's what mapping means. Okay, let's have a break, 10 minutes, stretch up a bit.